that there's a lot of writing and a lot of listening today. This is our final concept. It's called hypothesis testing. And we're going to do it for, guess what? Déjà vu. Single proportions, hypothesis testing for difference between two proportions, hypothesis testing for single mean, and hypothesis testing for the difference between two means. But we are not going to do 95 and 90% confidence intervals. So we're going to tackle this in a different way. So these are the main themes. We're going to look at what's called a null and alternate hypothesis. Then we're going to look at what are called left, right, and two-tailed tests. The Z statistic that is associated with a hypothesis test. A new guy you've never seen yet called a p-value. That is not the same as p equals. It's its own thing. It's called p-value, right? It's a new guy, very similar name. And we're going to show you, maybe not today, but eventually, how to calculate that p-value. Then conclusions about your hypothesis test. Essentially, conclusions are there's enough evidence to prove what you were looking for, or there's not enough evidence to prove what you're looking for. So we're going to look at the conclusion, and it's based on a number called the significance level, and that significance level number is called alpha. And alpha takes various values, but its most common values that it takes are 0.1, 0.05, and 0.01, right? And then we'll look at validity of conclusions and errors that can happen when you do this type of inference. An inference hypothesis test is an example of an inference. You're trying to infer the truth from some data, right? You're trying to say, can I say something's true from numerical data? We know that the world's not perfect, and statistics isn't either, but at least we can say, statistically speaking, we've proved this. And that's kind of what hypothesis testing is. It's a formal way of setting up a process where you try to prove or disprove something. So a hypothesis test is a statement, in this case, about a single population proportion, and that's called P, that we wish to test to see if there's any evidence that this proportion is true or false. So let's give you a story where we could look at this and how it gets applied. And it's very precise way it's written, but that's fine. Suppose that we knew, for some reason or other, that the population parameter P for, making this up, for the, it's a proportion, for the proportion people who like pickles is P equals 0.25. So suppose we did a census, or it's just common knowledge or whatever, that the population, the percentage of people who like pickles is 25%, right? And a scientist is saying, well, yeah, 20 years ago that was true, but that was then and this is now, to quote some song I can't remember, right? I wonder if it has changed. I think fewer people like pickles today than they used to. So our question, or our test that we want is there evidence to prove that fewer than 0.25 like pickles today? So you go to the government and you say, I need $20 million to conduct this test, because I'm going to have to, you know, do surveys and ask people and do all sorts of things. Plus, I want to go to Vegas. Could you give me this $20 million as to do my research? And the government says, yeah, here's your money, off you go. Now, if you think that is dumb, do you know that the government finances research on butterflies? Right? Go looking at it. There's some weird things out there. They've spent $100,000 finding out the distribution of a particular butterfly in a state. Look it up. Why they wanted to know, who cares? Government will spend money on some dumb things. So now that I've said that, I might actually try it. Can I get 20 million to find out if people don't like pickles? So back to the story.
The butterflies are probably for migration and global warming purposes.
What are those buggers heating up the world?
No, but they look at migration patterns and connect it to global warming and patterns.
Don't you get me
It's called the
started
butterfly
on
effect. Every flutter increases the temperature of the Earth.
No, I think she's been. Yeah, I do understand. I hear what she's saying. No, but if butterflies are good predictors of weather patterns,
they're not predicting it. I don't know. Butterflies have shown to have different migration patterns over the past few years because of different temperatures.
Yeah, I could understand that. So, okay. Maybe it wasn't such a dumb thing that they financed it. So back to our guy, which is a pretty dumb thing to finance, right? Is there evidence to prove that they're fewer? So what we do from this story is we set up what's called a hypothesis test. A hypothesis test is going to be a way of formalizing this. But before we do that, I want to make sure that we're clear on notation. When I use the number P, that represents the population proportion. If I use P hats, which I will eventually, isn't that my sample proportion? Right, we're all comfortable with that notation. I just want to make sure that we're clear on that, right? Now, back to this hypothesis test. There are two hypotheses. There's a guy called H naught, which is called typically the null hypothesis. And this is whatever it was, right? So whatever it used to be, and may still be. And then there's a second guy that is called the alternate hypothesis. And that is the new, what would I call that? The new statement. So in the example that we've just said, the null hypothesis is that the population of percentage of people who like pickles is 0.25. That's what it is in the past. And the alternate is that they're now fewer. In other words, the p-value for the population has changed, right? It's now less, right? And so this is the hypothesis test that we are going to do. One is, it's still 25%, and the other is, can we find evidence to prove that it's now less than 25? And you know that H naught and HA, that is very common. I don't like this notation, but you might see it if you go looking. I've seen H1 and H2. I did not like that notation. This one I like a little bit better. I've seen these two guys called H0 and H1. That one I could live with. That one I hate. So I'm not going to allow it to exist. But we're going to do this one. I like this notation, especially the A part, because it makes me think alternate, right? And I'm doing a quick check on what this book does, and we're good. They call it H0 and HA as well. Now, how do you think I could get evidence to see if this is true or not? Because it might be true, it might not. Well, I guess I could ask everybody in America, but it would probably cost me more than $20 million, right? So I'm not going to do that. So what could I do instead? How could I collect evidence to see what this value is now?
Could you do it by like seeing how much pickles are sold?
Oh, you could
How
do
many
it.
of them are?
That'd actually be a very cheaper way of doing it. Or couldn't I just conduct a survey and ask 1,000 people, do you like pickles? Right, which is typically what they do, right? They do a simple random sample. So that is essentially my start, right? Now, I go and I collect 1,000 people, and I find out that 0.24, right, like pickles, which, notice I'm using p hat because that represents a sample, right? And I could argue, but it's not a good argument. Hey, it's 24%. That's less than 25. I've proved what you thought was true. I've shown you that there's evidence to prove that they're fewer than 25. That on its own does not prove anything. You know, when you do a sample, don't they vary from one sample to the next? This particular sample just happened to be 24, but couldn't have done another sample and got 26%. And then another sample with 22 and another one with 25.1, and and so on and forever, right? So that is not good enough. That isn't considered evidence. We have to do a lot more work. Now, what we did in the past was, wouldn't we maybe get a 95% confidence interval and see what that interval looked like, and then we could maybe compare it against this guy? I mean, that might have been how we do it in the past, but we're doing this a little bit more formally now. So I'm going to take this guy, right? And somehow we're going to use it. Well, this brings me to left-tailed, right-tailed, and two-tailed tests now. When you're alternate, right? The new statement, a thing you hope to prove, right? Guess I should put that down as well. That you hope to prove is true, right? This new guy, right, generates a test. And that test, although you don't know what it is yet, is either a left, a right, or a two-tailed test. And they have names depending on what's happening here. In this case, I'm trying to prove that P is less than a number. And when you're trying to prove P is less than a number, that's called a left-tailed test. In a different world, suppose I was trying to prove that actually more people like pickles, right? That would be called a right-tailed test. And sometimes I just want to prove that it's changed. I'm not sure which way it's changed, but my alternate is either this guy, left-tailed, this guy, right-tailed, or this guy is called two-tailed. And a two-tailed test is basically, I believe it has changed. I don't know which way it's changed, but it's different from what it used to be. So far, so good. That's actually quite easy to do, right? Boom, boom, boom. There are only 3 choices, so you should be able to tell which it is. These names are going to become important when you use SALT, because you're going to use the software to calculate a lot of the stuff that's going to happen. Let's move on with my little story. So now I'm going to calculate what's called a Z statistic, or Now this Z statistic, very often we just call it Z, is P, take away P hat, divided by the standard deviation. And it's P, take away P hat, over the square root of P, Q over N. So this new guy, the Z statistic, here's my story, is this fella. So let's see what we have. P is always this fella here, right? Whatever the null hypothesis says P is equal to, make that P. Obviously, Q would be 0.75. P hat is whatever our sample has. In this case, P hat is 0.24. This fella here is essentially the standard deviation. And one of the most common mistakes that people make when they do hypothesis testing is that they don't use P and Q. They use P hat and Q hat, because haven't you been using P hat and Q hat a lot in confidence intervals? Remember, confidence is P hat, Q hat over N, that kind of thing. Have you noticed that it's the P value? It's this number here that you use, not the 0.24, but in this case, the 0.25. So it's going to be 0.25, 0.75 divided by a sample size, which is 1,000. So in this case, let's see what that guy comes out to be. It's going to be the square root of 0.25 times 0.75, and you're going to divide that fella by 1,000. And the answer for that fella is 0.0137, at least to 3 decimal places. So to get this Z statistic, it's P, take away P hat over the standard deviation. And P is 0.25, P hat is 0.24, and the standard deviation is 0.0137. And when I do this in my calculator, I'll put a bracket around the top. That way I get the order of calculation correct. And we now have a Z score of about 0.7299. Okay, about 7.3. There we go. So there's our Z statistic. And that takes us to here. So we had a story, and from that story, we set up the null and alternate hypothesis, and we decided, oh, which kind of test am I doing right now? A left, a right, or a two-tailed? For this story, left, right, or two-tailed?
Left.
Agreed? Wasn't our story, is there evidence to prove that it's less than this, right? And I have just screwed up, and I've just realized that. Yeah, fixed it. I got my P's and my P hats mixed up. My apologies. And I don't know why I did that. I'm just careless. It's basically data take away the mean over it. So it's P hat take away P. Please don't. Can you try? I mean, you know it's the same number if you switch them around. That was annoying. I was doing so good here. So we're doing a left tail test. And so we're now going to calculate the p-value. So after a little fix, we found out that the Z statistic was that number. Now, I'm going to draw, just because it helps visually, what the normal distribution looks like. There's Z. Negative 0.73 is about here. And we are going to find this guy that's shaded on the left. Can you see why it's called a left tail test, which is why I knew that I got my formula wrong? Isn't that the left-tailed, right? Now, the new guy called the p-value, right, this fella. Typically, we're going to use salt, and I will. It's the probability that you get a Z-score, in this case, less than negative 0.73. So what we're calculating with the p-value is how unlikely is it to get the result that we got, right? The 24% out of 1,000. How likely is it that we would have got that result by just sheer randomness? And so the argument goes something like that. If this p-value is really tiny, right, really small, then we can assume that it wasn't randomness. The reason that it was a smaller value is because the population really has changed and now it's smaller. So evidence here is a tiny p-value, right? Really small p-values are the kind of the bread and butter of this technique. If the p-value is tiny, it means the reason your sample is what it is was not just the randomness, right, that you get when you do samples. It was so small that it wasn't randomness. It happened because it was true. By that I mean the alternate was true. You know, it's less than 24%. So we're going to get that guy, and we're going to do it using salt. So let me find salt. Oh, darn it in space. I've lost my window. Give me a few seconds to find my salt window. Where the heck are you? Is that you? Okay, use salt. That looks good. Gotcha. Okay, I found my salt window. Right. So, are you looking at normal distribution, fella, right? Okay, so when you hit the salt button, make sure, I don't know if I can make this a little bit bigger. Well, just for a few seconds so you can see what I picked. Do you see that I chose distribution calculations? Because there's lots of things you could choose, but choose that one. Now, normal distribution, 0 and 1. They are never going to change, right? They're 0 and 1 for every hypothesis test, so leave them alone. So far, so good, right? Now, click on left-tailed. Remember it was a left-tailed test? Click on left-tailed. Go over here and put in that Z-score that I just got. And the Z-score I just got was negative 0.73. And when I click out of that, do you see this number here, right under it? Maybe I could make it bigger again to show you. See this guy here? He is the p-value. What that is saying is the probability that you get a Z-score less than negative 0.73 is going to happen about 23% of the time, 0.2327. Okay, I don't like decimals. I can live with them, but I don't like them. I prefer 23.27%. Right. In other words, if the original null hypothesis was true, if this was still true, you would expect to get an answer where the sample was 24%. You'd expect that to harm, or even lower, about 23% of the time. Would you agree that's a pretty high percentage of the time? That could well have happened just by randomness of samples. So we do not have evidence. But you're going to say, well, how small does it need to be before you're going to say, this wasn't randomness, this guy here is really true, it is less than 25%, it has changed. Well, we don't let people just decide on their own how small the things are. We have a guy called significance level. And the significance level is either 10%, 5%, or 1%. If you've ever seen scientific medical reports that have used statistics, you might see p-values written down, like the p-value was 0.03 or the p-value was 0.17, right? Things like that. And now you're wondering what that was when they say p-value. They probably should say p-value, but they very often just say p. What they're doing is they're telling us essentially this guy here. Now, how does the test work? Well, you have to decide which one of these significance levels you are going to choose right at the start. So see, when I was up here deciding who my null and alternative, I should have chosen a significance level. So let's pretend that I have, and I chose the 5% level. Then our conclusion is based on this. Is our p-value less than the significance level? In this case, is 0.2327. Is it less than that? And the answer that we can see in this case is no, it's not. So the conclusion that we're going to come to is that there's not enough evidence to prove that people like pickles less than they used to. Now, if this p-value was small, right, and small means in this case anything less than 0.05, then the answer to this question would be yes. And when the answer is yes, you can then go and say there is evidence to prove that there are fewer than 25% of people like pickles today. And you should say, if you're being really honest, with a p-value of whatever it is, let's pretend it was that number, and using a significance level of 5%, you should have that as part of your statement at the end. So this particular one, this hypothesis test that we've just done, came to a kind of boring conclusion. And that boring conclusion is there is no evidence to suggest that people like pickles less than they did in the past. And you have to be quite picky about the choice of words here. Do you know there is no evidence to suggest that people like pickles less than they did in the past? That's what the analysis has said. That doesn't mean that it might still be true. It just means that I haven't managed to prove it. Analogy. Can you imagine that there's some people who have committed crimes, but when they go to trial, they get off? Now, the reason they got off wasn't there not enough evidence to prove they committed the crime? That's not quite the same as you didn't commit the crime, if you really think about it, because many of the times it does, right? Many of the times if you get not guilty, it's because you never did it. But isn't there a percentage of times where that is wrong? Right? They did commit the crime, but there wasn't enough evidence. So if you think of the analogy here as the pickle story is a crime, was the crime that it's less than 25%? Well, we didn't have enough evidence to convict you, so we can't say anything. Have we got the theme of how this process is going to work? So I'm going to see if I can create one from scratch. Only this time I'm going to get one that actually is significant, right? I'm going to see if I can make that happen at least. So let's suppose we asked people in the past, have you ever flown on an airline? And we asked them, oh, I don't know, 20 years ago. And the answer that came up was, in the past, 35% of people had flown, right? Okay, maybe 50 years ago would be more realistic, right? 50 years ago, have you flown in a plane in the last year? And 35% of the people said yes. And then they asked people this year. And they conducted a sample. And it was 300 people. And the percentage who said that they had actually flown on a plane was 20% because of COVID, right? So we want to see, is there evidence actually to prove that people have changed their flying habits because of COVID, right? So I'm picking one that I know should be significant. So the null hypothesis is that it's still 35%, right? What it was last year or whatever. And the alternate hypothesis is that it has gone down. Is this a left or a right tail test? Left again, agreed. What significance level are we going to do on this one? Well, I could do a 1, a 5, or a 10%. We really should decide now before we do anything else. And that's very often up to the researcher. So what do you want? 1, 5, or 10?
1.
So we are going to be pretty sure if we convict this guy that he's guilty, right? I guess we could phrase it like that, right? That'd be the knowledge. So based on what we've got here, I should be able to create all the critical values that I'm looking for. Just want to make sure I don't screw it up this time. So we want to get our Z-score, and it is P hat, take away P over the square root of P Q over N. So P hat is 0.2, P is 0.35, and that guy is this fella. So it's a 0.35, a 0.65, and it was 300. So that's going to be negative 0.15 on the top. And on the bottom, I'm going to get the square root of 0.35 times 0.65 divided by 300. And on the bottom, it's 0.028. So negative 0.15 divided by 0.028 gives me an answer of negative 5. Make it 4. Now I'm going to get the p-value. And the p-value is the probability that you get a z-score less than negative 5.4. And I'll zoom over to our SALT window, which is kind of already set up. And I should be able to get that value. So I'm looking for a left tail test, so I don't need to change that. That's perfect. Actually, you can see looking at that, I mean, pretend that X said Z, right? And you're well on your way. So I want it to be less than a number like 5.4. And I get a really interesting answer. Don't worry about that little exclamation mark.
We're not seeing anything.
Oh,
I'm not.
I thought I'd got through to it. Okay, let me off and on again. There. Can you see it now? Okay. So I put in the negative. Stop doing that. I put in the negative 5.4. And the answer I got was 0. So the p-value here is 0. That's pretty small. Would you agree? That's like overkill small. But that's good news. So I got my p-value and it's 0. Can you imagine that most of the time it's going to be 0.062, 0.17, right? It's going to be a number, but I just did, well, actually I should have guessed that. Can you remember Z-scores way back in the day? What was the usual range for Z-scores? Roughly, -3 to +3, right? In fact, isn't 99.7% of the time that's what a Z-score looks like? So can you imagine a Z-score of -5 is like way out there, is really, really, really unusual. And that's why we got a 0. Technically, it's probably 0.14 zeros and a 7, right? But it rounded off. But we are good. Now I can do my test. Is my p-value less than significance level? Is 0 less than 0.01? And the answer is yes. So I can now say, and this is the fancy way of saying it. Well, first the English way, then the fancy. There is enough evidence to prove that people are flying less right now. Okay. Now, what's the formal way of doing it? This is a sentence that you'll see in textbooks. There is enough evidence to reject H naught. And so HA is true. So what they're saying is there's enough evidence to prove, where's my little piece of paper? There's enough, I lost the damn thing. Oh, here it is. There's enough evidence to prove that that isn't right, to reject it essentially. And therefore this is true. So whenever you see research papers, it could be social sciences, it could be medicine, it could be in physics, this hypothesis testing structure that I'm showing you right now is pretty much the bread and butter way that they come to conclusions that everybody in the world agrees to, because these have been set out like carved in stone. If you want to do a test, if you want to prove something to me using samples and statistics, you got to set up a null alternate hypothesis. You're going to have to choose a significance level. You're then going to go out and collect your sample of data and make sure you do it, fairly and unbiased and all the other stuff. You're going to come up with your p-hat, you're going to get your z-score, you're then going to get your p-value, and then you're going to do your test. And if everything works out well, your p-value will be less than alpha, and you will be able to prove what you were hoping to prove, right? That people eat pickles less, or we fly less, or that there's an increase in temperature in the world, or a decrease in temperature in the world, or whatever it is you're trying to prove. And if you unfortunately get a p-value that's just too big, right? It's bigger than this number. All you can say is that there's not enough evidence to prove what you were hoping was true. And it doesn't mean that what you were hoping to be true isn't true. It just means you haven't found enough evidence. So to finish with, I haven't talked about my last thing in the list. Validity of conclusion and errors that can happen. Do you know that we picked a significance level of 1%, right? That was done right at the start. Can you imagine an unscrupulous person waiting to see what the value of their p-value was, and then retrospectively picking the significance level alpha? In other words, you got a p-value of 4%. Won't you pick a significance level of 5% so you can say, I've got evidence? Or if you got a p-value of 9%, can you see someone picking a significance level of 10 so that it would be less than it and so significant? Would you agree that is unprofessional, to say the least? That you're choosing after you've done the research what the significance level is. If you're being totally honest about it, shouldn't you just pick this guy and stick to your guns? If it doesn't come out the way you do, you just say, oh, well, that's life. But that has been, that happens, unfortunately, quite a lot. How can you tell? Well, see if they're doing more than one experiment with different sets of data. If you see the significance level shifting, like in experiment 1, it was 10%, in experiment 2, it was 5%, in experiment 3, it was 1%. Isn't that kind of suspicious? Shouldn't it be 5% all the time or 10% all the time or whatever? So that's the validity. Is it really, you know, are you really being honest about your process? And sometimes that means you spend a lot of time on something and then at the end of the day, you haven't managed to find evidence that it's true. Now, what kind of errors can happen? I have seen stories, I don't believe they're true, they're probably internet stories. But can you imagine you conduct an experiment and it doesn't come out with any evidence? So you throw that data away and you pretend it never happened. And then you keep on doing it until one day you get an experiment where the data does work. And that's the only one that you publish. That's basically cheating, isn't it? And in fact, do you know if you do something, you know, if you do something often enough, and what's the analogy? Keep asking the question till you get the answer you want. If you do something often enough, won't you eventually just get a rogue set of data that will prove what you're looking for? And that is definitely a no. You can be a bit generous about moving the significance level, right? From 5 to 1. I wouldn't do it, but you can kind of let that one maybe slide a bit. But only showing the evidence for the ones that you have done that are successful. Those things always get caught out. Someone in Japan conducts an experiment and gets evidence to prove something's true. That doesn't become common knowledge in the science world. Scientists are pretty skeptical people. So what happens is that a university in California and maybe one in London conduct the same experiments and collect their data, and they test their data out. And they come back and say, well, we did the same experiment as yours, and that fission reactor thing that you said is true. I'm not getting that data. The one I did said no evidence at all. And then the guy in London says, well, we did it and we never got evidence. And so that would be a signal that either that person was just unlucky or they cheated. But what happens if California do it and it's significant and London does it and it's significant? Do you see we've now got a body of knowledge where 3 different independent groups of people have conducted some experiment and all of them have came up with the same conclusion. Then it becomes scientifically accepted, and it becomes the new norm in science, whatever that new norm is. And that is how we work with truth, which is a very fleeting thing in the science world. We do hypothesis tests. And I've overshot your time, and I apologize for that. Have a nice day. Say hi and bye-bye if you haven't already.